Yeah, good morning to all of you. In this lecture, I am going to discuss the concept of Lagrangian. So, Lagrangian is play a very important role to analyze the analytical mechanics or classical mechanics, which is a scalar mechanics. So, Lagrange basically developed a mathematical tool to analyze the trajectory or to analyze the mechanics of particle analytically or in scalar way. So, basically Lagrangian is defined as, mathematically it is defined as L is L QK dot and time explicitly, where QK, I have already discussed the concept of constant, generalized coordinate and degree of freedom. So QK is a generalized coordinate. This is generalized coordinate. If generalized coordinate is QK and QK dot is simply dq by dt, dqk by dt. This is generalized velocity and this is time. So this QK is basically generalized coordinate and this QK dot is basically dqk by dt. And generalized, what is generalized coordinate? Generalized coordinate is minimum, very important keyword in classical mechanics. So this is the minimum number of coordinate which specify the motion of our dynamical system, and it is equal to the degree of freedom. It is equal to the degree of freedom. So Lagrangian, basically Lagrange developed a mathematical tool to analyze the mechanics of particle or to analyze the analytical mechanics of particle or dynamical system. So he developed the mathematics and he defined Lagrangian, which is L equal to, which is function of generalized coordinate, generalized velocity and time. It is also defined as L is basically T minus V. This T is kinetic energy and this V is potential energy. So this kinetic energy, we know that this kinetic energy is half mv square, or we can express our kinetic energy in terms of generalized velocity. So we can write it as half m qk dot square, because qk is a generalized coordinate having dimension of position. So qk dot is velocity. So this is, and v is simply, this is potential. Let me write, this is kinetic energy and this is potential energy, energy due to its position, which is VQK. So this is the way to define the Lagrangian. Now next we will discuss that if we have how to express the Lagrangian in different coordinate system. Because coordinate system, and we know that there are three well-known coordinate system. One is Cartesian coordinate system, that is XY coordinate system, and there is spherical polar coordinate system. In 3D, in 2D it is polar coordinate system and cylindrical coordinate. So let us express our Lagrangian in different coordinate system. So Lagrangian in different coordinate system, which is, so Lagrangian in different coordinate system. First, Cartesian coordinate system. That is x, y and z. What is our L? L is simply T minus V. T is simply half m qk dot square minus V qk. Then what is qk in x, y, z? This qk is simply, so we can express half m x dot square plus y dot square plus z dot square minus v x y z. This is simple expression of Lagrangian in Cartesian coordinate system. Second, we can express our Lagrangian, let's say this is B, L in spherical polar coordinate system. So L is again T minus V, which is 1 by 2 m r dot square r square theta dot square plus r square sin square theta phi dot square minus v r theta and phi. V r theta and phi. So this is kinetic energy term, and this is kinetic energy, and this is potential energy. We know that how to express our x, y, z. There is a relation between x, y, z, Cartesian and cylindrical coordinate system. What is that relation? Relation between x, y, z and r, theta, phi. So x equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z equal to r cos theta. So using this equation we can convert our x dot is basically dx by dt. X dot is basically dx by dt, y dot is dy by dt, z dot is dz by. So if we have a profile of Lagrangian in Cartesian system, which is this one, so we can express, because there is relation between these coordinate system. So for a spherical polar coordinate system, there is a relation between x, y, z and r, theta, phi. So I am not going to derive this, because those who are interested, I will give you the reference book, which is DJ Griffith, Introduction to Electrodynamics. So this is very good book. You can see how to express different coordinate system and what is the relation between x, r, theta, phi, x and different coordinate system. So just go through this book, you will get this beautiful relation. So this is way you can express your Lagrangian in different coordinate system. So in spherical polar coordinate system, our Lagrangian is this r dot is simply dr by dt. This theta dot is d theta by dt, and this phi dot is simply d phi by dt. So Lagrangian, we have Lagrangian profile in spherical polar coordinate system. Next we have a cylindrical coordinate system. C. So L in Lagrangian in cylindrical coordinate system. So what is relation? Again there is a relation between spherical, there is a relation between x, r, theta. What is the relation? And what is cylindrical coordinate system? X, y, z. If this is, so there r, phi and z. This is Cartesian and this is cylindrical coordinate system, r, phi, z, because I am just following the standard symbol of DJ Griffith, Introduction to Electrodynamics. This is very good book. I will recommend this book. So just go through to this book in order to analyze the concept of coordinate system. There is a beautiful picture. So just go through in this book and you will see the detailed derivation that what is the relation between x, y, z and r, theta, phi. So in cylindrical coordinate is r, phi, z. And spherical is r, theta, z. So in this coordinate system, our relation x is simply r cos phi and y is r sin phi and z is simply z. So Lagrangian in this coordinate system is simply 1 by 2 m r dot square r square phi dot square plus z dot square minus potential is simply r phi z. This is general profile of potential. I am not talking about the special potential. This is general profile. It could have any profile. For gravitational potential we have different profile. For Coulombian potential we have different profile. So depending upon the situation we have different profile of this V. So this is the Lagrangian for cylindrical coordinate system. This is the Lagrangian for spherical. So this is L Cy cylindrical, this is L Cartesian, and this is L spherical. So we have three different profile of Lagrangian. So depending upon the system we have different profile of Lagrangian, and once we know the Lagrangian then we can predict each and everything about the dynamics of our particle, or we can predict each and everything about the mechanics of particle. So Lagrangian is a very important tool to analyze the mechanics of particle. So it's all about the Lagrangian. Let me just quick revise. Lagrangian basically it is defined as T minus V, kinetic minus potential. It is a function of generalized coordinate, generalized velocity, where generalized coordinate this is kinetic energy half mv square, or in terms of generalized coordinate this is mqk dot square, and potential is function of generalized coordinate. And this is the Lagrangian in different coordinate system. In Cartesian we have this profile, in spherical we have this profile. We can derive this relation also from Cartesian coordinate system, because we know how to express our x. In this case our x is a function of r theta phi. So dx by dt is, we can use chain differentiation rule. So differentiating, taking first function, second function, so you can obtain or you can derive this relation. So this is Lagrangian for spherical polar coordinate system, this is Lagrangian for cylindrical coordinate system. So in next lecture we will discuss that if we have a profile of Lagrangian, then how to find out the generalized momenta, or how to check whether the given coordinate system is cyclic or not. Thank you.